Hello all! Okay, this time we're working into Recitation Week 6. What we're looking for here is a continuation of what we were talking about with acids and bases. So again, I've marked a few things we'll go through exclusively in recitation, and the things that are left over we're going to go through right now. So the first thing is identify the acid, base, conjugate base in the following reaction. So this is kind of a continuance of what we saw in Recitation Week 4. As well as a continuation of what you've learned in lecture. So when we're talking about identifying an acid, I always look for something in terms of a Bronsted-Lowry acid of what is going to donate a hydrogen. And then when I think of a base, I always think what is accepting a hydrogen. For the conjugate versions of those, I basically just reverse the reaction and say, okay, in the other direction, who is going to accept a hydrogen and who is going to donate a hydrogen? So in the forward reaction, we're looking for the acid and base. And so in this case, I have NH3, which then becomes NH4+. So in this case, it has accepted a hydrogen. It has one more hydrogen. So this here is my base. And then when I see HCl here, this becomes Cl, which means it donated a hydrogen. So this is my acid. All right, now to find the conjugate acid and base, I'm just going to work in reverse. So Cl- becomes HCl, which means it accepted a hydrogen, making it a conjugate base. And then, of course, what must be left, what we can always double check with our own understanding, is I have NH4+ that becomes NH3. So in that case, it accepted a hydrogen. So it donated a hydrogen to something else, so it must be a conjugate acid. All right, which is good because that's all the things we needed to discover. So we've done this well. All right, next, calculating the pH of a solution when it gives us the concentration. Well, we know that when we want to calculate the pH, we basically just take the negative log of the concentration of hydronium ions. And the reason we do that is because we know that by taking the negative log, we are finding out how many hydrogens have been used up. And that is in turn how we find the concentration, in which case pH is measuring that. So we also know that the 10 to the negative pH will equal the hydronium ion concentration. Another way of doing it. So in this case, because we have the concentration of hydronium ions, I'm just going to take that and plug it in here. And when I take the negative log of this number, I look over at my calculator, I get the number of 3.16. So there we go. Kind of the same idea with 4, part A, so I'm going to skip over that one and go through it in recitation exclusively, and then we're going to move into 0.10 molar of HCl. So the one thing is when we've got a actual molecule here as an HCl, we've always want to see it as how it's broken down. So in this case, it's going to break down to H+, or hydronium ions as well, are also known as H+ in some cases because there's always water in an acid-base reaction, and then Cl-. And so these are in a 1-to-1 ratio. And that means that the concentration of HCl is going to equal the concentration of H+, or as H+ is synonymous to H3O+. So I literally just have to take the negative log of this given concentration, 0.10. And when I take that, it'll give me my pH, which when I do, I look over at my calculator here, and I get I get 2. The only time it's not a 1-to-1 ratio is when you'd have a different amount of hydrogen there. So say you've got H2SO4 for sulfuric acid. Then you'd have to watch to break this down and note that the concentration is no longer 1-to-1, but 2-to-1. So something like that. Oh, sorry, this has no charge on it. It's neutral. All right, moving on. The pH of Coke is 2.52. So what is the concentration of hydronium ions? So again, if we just take 10 to the negative pH, that is going to equal our concentration of hydronium ions. So if I literally just take 2.52 or 10 to negative 2.52, plug that into my calculator, and then I get 3.02 times 10 to the negative, and I count my zeros, 3. Okay, so that's going to be our concentration. Easy peasy. Moving on to number 6, how does adding each of the following salts to a solution affect the pH? Best thing to do here is break this down. So I know that KCN is really potassium, and I know that CN minus is cyanide. So when I think of potassium, I'm going to think of a strong base. Things like NaOH are a strong base. Things like KOH are strong bases. So this came from a strong base. CN minus, or cyanide or hydrocyanide, that's a weak acid. And so when you're working with a weak acid and a strong base, the weak conjugate acid means that there was a very strong acid to begin with, or it's going to occupy that. And so in that case, the weak acid means that there must have been a very strong base. And so by adding these salts in, essentially what you're going to get is an increase. So at a strong base, and remember, strong bases are going to increase the pH, because when we think of base, we have to think of higher numbers. So anywhere from 8 to 14, right? Now CaCl2, Ca2 plus actually came from a strong base, and then Cl minus came from a strong acid. So when you have a strong base and a strong acid, it means that you're really just creating water and salt. And so that means that things are going to be unaffected. Finally, we have ammonium ions, so NH4 plus, and that comes from a weak base. So we have a weak base here, and then we have Br minus that came from a very strong acid. So again, if we have a strong acid, that means that by adding these salts, we'll probably decrease the overall pH. Okay. How does adding an acetate anion to water affect the pH? So again, we're just having to think about in general what is going on. So when we think of pH, we have to think about the concentration of our H+, because that's what's being measured here, right? Like when we think about pH, it's always concentrating on this hydronium or the H+ concentration. And so when we think of that, we just have to think, if I'm going to add something that has this negative charge on it, that's definitely going to attract H+ ions to it, that's going to take up H+ ions, and in doing so, it's going to increase the overall pH. So by adding something with a negative on it, it's going to occupy hydrogens, take hydrogens out of concentration, lowering the concentration of hydronium ions, and in doing so, overall increasing the pH. All right? Okay. Finally, with number 9, because we're going to go through 10 in recitation, predict the direction in which the equilibrium lies to the reaction and explain your reasoning. So we don't have to do any math. So anyone who's thinking, oh my gosh, I see a bunch of Ka values having to do math, we're not going to have to do that. What we have to do is specifically look at this number and compare it to this number. So, I didn't get this over all the way. So it's saying which side of equilibrium. So we've only got the left side and the right side. And I can see here that HF, this number is going to be associated with our left, and our acetate is going to be associated with the right. So we're just comparing these, and we've now aligned them with each side of our equation. And now I'm going to say, okay, 7.1 times 10 to the negative 4 is greater than 6.5 times 10 to the negative 5. So what we know about Ka values is the larger the Ka value, the more it's going to dissociate. So this one is going to dissociate a lot. So I'm going to put a lot next to it, or a lot. And the one that's smaller is going to dissociate less. So I'm going to put less on here. When we think about equilibrium, we're always thinking about who has more and who has less. So in this case, the right side has less, and the left side has more. And every time when we think about equilibrium, all you have to think of is who is going to want it more. And then always it's going to be the one that has the least. So since the right side has less than the left side, the equilibrium is going to shift towards the right. And that's because it's going to want to make up for its lack of having those ions in availability. So it's going to shift towards the one that has the lower Ka value. That's because, again, if you have a lot of something on one side, equilibrium is going to want to make the forward and reverse rates equal. And to do that, you're going to want to get them to equate to each other. So if one side is not making as much, it's going to shift to that side in order to help it make as much. So that's why it's shifting to the right. Okay, guys, thank you so much, and I will see you next week.